Hello everyone, today I'm going to present my work, Learning to Summon 3D point cloud in 2D image space. Please visit our GitHub page if you are interested in. Our work addresses the following question: how to extract local pattern from the point cloud. In the existing works, point-based method extract point cloud features by applying multi-layer perception followed by pooling layers, which are missing local pattern learnings. Graph-based methods try to extract local pattern through graph convolution on k nearest neighbor graphs, which however are complicated to train. In this paper, we are trying to project the 3D point cloud into a 2D image space so that we can take advantage of local pattern extraction in conventional 2D CNNs or point cloud simulation. By employing the graph drawing technique, the image representations of 3D point cloud keep most of the local pattern between points, which are explicit to the well-studied 2D CNNs like GoogleNet, ResNet, and UNet. Specifically, we take 3 steps to solve the problem. Firstly, we use de Liuning triangulation to build a graph from the point cloud. Secondly, we modify the command QIE, a graph drawing method, to plot the graph onto an image space and assign them to specific image pixels. Next, we apply UNet, a well-known CNN for image simulation, on our point cloud image to estimate segment labels, which are at last returned to the point cloud segment. The Liuning triangulation tries to separate the 3D space inside the point cloud into tetrahedrons, whose vertices are all from the point cloud. A graph is then constructed by grouping the vertices and edges of the tetrahedrons. Compared with the KNN graph, the Liuning triangulation better perceives the 3D structure of point cloud and generates a more meaningful graph. The second part, graph drawing, tries to plot the point into an image space while best keeping the geometry pattern. As we see in object function, the method tries to minimize error between Euclidean distance in the image space and half distance in graph space. This method is good at creating point cloud images, but takes too much time. To accelerate the process, we propose a hierarchical scheme that maps the point layer by layer. Initially, we use k-means to separate points into clusters, and then we generate images from each cluster and cluster centers. Finally, we embedded cluster image into the high-level image, and then we get the final image. For segmentation, we apply UNet on the point cloud image and estimate the segment labels of each point. Since we know the position of each point in the image, we can easily build a lookup table and project the image segment back to point segment. This is the implementation of our all works. As we see, we separate point cloud into small parts, generate the point cloud image of each of them, and embed them together using high-level image. Next, we use UNet to perform image simulation and return them back to the point cloud segment. Our method achieves CVPR in Xinming path simulation benchmark. In both critical mean instant of union and instant mean instant over union. When we look at the example result of a skateboard, we can see that our work better segments the front wheels and the board because it will encode the geometry pattern in local regions and point cloud image. We're WRI with Lab. Thank you for listening.